My name is Alexander, and I'm a PhD student at Lancaster University. And in this presentation, I'd like to present to you Wayfinder, research and tooling done in collaboration with Lancaster, the University of Manchester, and NEC Labs Europe. In this talk, we'll attempt to navigate the benchmarking and performance tuning of OS configuration. If you're watching this, you'll either be a part of or at least aware of the enormous amounts of systems work that's ongoing, not to mention here for ACM AppSys, towards increasing the performance of applications, especially under specific use cases. We'll start with our premise, and that's that tuning OS performance is tough. And the research community knows this, seemingly just by the sheer amounts of work that's being done to squeeze every little bit to get maximum amount of performance from the OS and the applications which run on the OS. Almost always the work is done in the result of countless hours of trial and error and often manual measurements and to know which configurations options matter most. And if we're gearing towards performance, we focus our attention to library operating systems and unikernels as our primary example. Heralded as a bit of a gold standard for performance, the unikernel promise of a specialized OS stack claims its rank by allowing us to build and configure the application and library operating system to any and all of its configuration needs and possibilities. Practitioners of library operating systems and unikernel builds face the additional considerable challenge of having to tune the unikernel to obtain the best performance possible. This is a bit of a dark art where experts in the field tend to know, though through lots of trial and error and experience, which parameters matter most and where appropriate values they should be set. The unikernel community, to say nothing of non-experts trying to use unikernels for the very first time, does not have, as of yet, a mechanism or tool to sift through a reasonable amount of these options in order to obtain high performance. Let's think of even a small example, using the library operating system and unikernel software development kit Unicraft to run Nginx. A combination of at least 3,000 possible configuration options are available. It's difficult to know which, if all, options are most important for a given use case for Nginx as a unikernel, and which ones have the most importance. Of course, again, we can use our better judgment and guesses, estimates, and a bit of greasework, but this is not systematic and nor is it scalable. To understand why this is important, when we look at our variance for possible performance for even just one unikernel project, OSV by Cloudius Systems, amongst the literature we find that the measurements performed for boot time and memory usage varied between 3 orders of magnitude. Along with just the sheer amount of configuration space for a particular OS or application, we wanted to understand why there was so much variance. And it's more than simply the configuration of the application itself. Yes, there's lots of configuration, but it's also how the benchmark was performed. Traits about the experiments and the benchmark and how they were run have many attributes that were left unanswered. For example, whether ASLR was disabled, what type of caching was used and where, what things were run in RAM, was anything pinned to any core, what was the governance mode for the core, was it set to performance or power saving, which tools were used and how, what were the hardware specifications, kernel version, what were the versions of the software used, so many variabilities and so many unanswered questions. And oftentimes, not all these questions were answered equally or consistently amongst the literature. This brings us to our first research question we aim to answer in this presentation, and that is it possible to automatically and intelligently derive optimal OS configurations for a particular application? Ideally, we would like users to simply select a target application and then let the system run a battery of experiments and sort and discover, hopefully in the shortest time possible, an optimal set of configuration options. And our second question is it possible to automatically gain insights into which options matter most? Yes, though through trial and error, experimentation, and some common sense, we know that certain configuration options really matter in terms of performance. For example, disabling access logging on Nginx or enable batching on a network stack. But would it be possible for an automated system to return a list of such options, or combinations of options, such that we could learn about the influences of performances automatically? This is especially useful for new applications with little to no standardization or common research. So we are struck with a balance for a system of fair head-to-head OS performance tuning by configuration, which is both idiomatic yet flexible, consistent yet allows for diversity, can return fast answers and yield the machine at work to full force with parallelism, yet remain accurate, to be repeatable, and of course, to be efficient. To this end, we present Wayfinder, a unified framework for deriving optimal OS configuration. Wayfinder is a novel, generic, and modular OS benchmark platform to accelerate how OSs are evaluated, compared, and adopted. Wayfinder consists of a modular subsystem that allows for plugging different search algorithms for deciding which configuration options to explore at each turn. We demonstrate the capabilities of Wayfinder and a use case based on Nginx, using Wayfinder to automatically find a performance optimum. We had 4 primary design goals for Wayfinder. The first is to provide reproducible benchmarking experiments for library operating system experimentation and to allow for a full automation of the performance measurement process. The second is to provide automated methods to efficiently explore the vast design space offered by modern library operating systems. The third is to efficiently leverage the parallelism inherently in multi-core systems to speed up the tests while avoiding noisy neighbor effects arising from co-locating sensitive performance measurements on compute units sharing hardware resources such as caches. And the fourth and final is a modular architecture which enables the extensibility of various components, in particular for new user-defined exploration strategies, for new benchmarks, and for new library operating systems. At a high level, Wayfinder addresses these design goals requirements by first automating the entire evaluation process and uniquely describing each experiment through a configuration file, a YAML file, thus making them reproducible. Another part of the architecture is to offer 3 automated design space or exploration strategies. The first is grid, the second is random search, and the third is Bayesian optimization through the scheduler. Another one is to allow users to specify the required degree of isolation via host configurator for each test to automatically infer the possible parallelism between tests. And our final design goal as part of our architecture is to offer convenient APIs so users can automatically customize parameterization process and to extend Wayfinder support for new exploration strategies, new benchmarks, and OSes. Wayfinder is programmed through a configuration YAML file, which starts with a list of configuration parameters to be varied and how they should be varied during the experiment. In this example file, we have 2 parameters, A and B. A is an integer, which varies between 0 and 12 by steps of 4, and B is a string, which has 2 options, hello and world. The most basic search, grid search, would simply generate a complete permutation matrix of possible combinations for the 2 parameters A and B, such as described in this graph over here, or this table. Parameterization is also quite flexible, and you can vary the number of parameters for either build time, such as whether you wish to bake in to the unikernel a network stack size, or runtime of the experiment, such as whether you wish to vary the number of clients during a stress test. After parameterization, Wayfinder has a list of defined jobs. There are 2 job types for Wayfinder, builds and runs. During a build, a single permutation of a set of parameters are set and are available as environmental variables for the build script. In this example, you can see how we reference a remote Docker image which creates a file system we can use during the build. When the image is instantiated, it is instantiated as a process and scheduled appropriately. For runtime jobs, which perform the experiment, we can mount additional paths such as the KVM Unix socket location and define a number of cores needed for the experiment. This experiment requires 3 cores, which we will focus a little bit later in the presentation, and uses them appropriately. Adding new benchmarks or OSes to Wayfinder is pretty straightforward. Introducing new benchmarks is as simple as writing a script to build the OS for the particular benchmark and to script the execution process that is to do the experiment. When we launch an experiment with Wayfinder, it takes care of setting a number of host environments to ensure consistency between experiments, such as disabling ASLR, setting the CPU governor, disabling caching, etc. In order to demonstrate the ability of Wayfinder to automate the configuration space exploration, we use a web server library operating system based on Unicraft and its Nginx port. The resulting project exposes 275 configuration options across multiple libraries, including the network stack, the scheduler, and the Nginx application. As the exploration space is prohibitively large and several parameters are numeric, we focus our analysis on a small set of network and application parameters, specifically the parameters you see here. Based on these parameters, Wayfinder automatically generates 512 unique library operating system images, reflecting all possible configuration permutations. Using WRK HTTP performance tool, we generate a steady stream of HTTP requests for a static page of 612 bytes and measure the average server response rate. In each experiment, we configure WRK to use 30 persistent HTTP connections, each running on a separate thread. As you can see from the figure, Wayfinder demonstrates significant impact that the library operating system configuration options can have on the performance. Different configurations can result in a range of performance from 239 requests at the lower bound and over 100,000 requests on the upper bound. We also show that the default configuration for Nginx on Unicraft, and we have a 33% increase from this default, showing that basically defaults aren't necessarily optimal. When we study the figure a little bit more closely, we can see the significance of certain options. For example, whether logging was enabled. So on this side of the graph, logging is enabled, and the other it wasn't, and we get better performance when it's turned off. We also see where keep alive timeout is enabled, whether heaping or polling mode is enabled, and the best performance is obviously when heaping or polling mode is enabled and keep alive timeout is enabled, and there is no logging, of course. So, given the large exploration space on modern machines, Wayfinder is faced with the conflicting goals of leveraging parallelism on multiple cores to run as many jobs as possible simultaneously in order to minimize the experiment runtime, and avoiding the noisy neighbor effects which occur when co-locating jobs on compute units sharing resources. For example, hyperthreads on the same core or cores sharing the same cache. While some jobs such as memory-intensive benchmarks would negatively affect each other on co-located, others such as build jobs or memory usage measurements would not. To maximize performance while maintaining performance isolation for the jobs which require it, you can declare for each job the level of isolation required for the execution job. We define 5 levels of isolation. Even if the configuration space for Nginx experiment is relatively small, 512 configurations, it takes 9 hours to complete. Wayfinder implements exploration strategies whose goal is to find the vast configuration space and optimum in as few steps as possible. We evaluated the capacity of our 3 exploration strategies, grid search, random search, and Bayesian optimization, to find the optimal configuration for the Unicraft Nginx search space. For each strategy, we vary the number of configuration that can be tested before ending the search and reporting the tested configuration given the best performance. This number is set at 10, 40, and 100, and the figure shows the maximum Nginx throughput found on the average of standard deviation of 10 runs for each strategy for each number of iterations. For grid search, the starting point is randomized for each run. Even with a large number of iterations, the naive grid search rarely finds the configuration close to the maximum throughput possible. The relatively good performance of the random search are due to the small size of the design space. So, given a larger space, random search is unlikely to yield good results, with the number of iterations is a small fraction of the entire space. Unsurprisingly though, the Bayesian optimization gives the best performance, consistently finding the best configuration, or at least close contender, even with a small number of iterations, 40 being 8% of the 512 configurations constituting the entire design space of the Nginx experiment. So this actually demonstrates the capacity of Wayfinder to quickly find an optimum in the vast configuration space offered by today's OSes by selectively and iteratively scheduling particular parameterized combinations. The ability of Wayfinder to parallelize experiments, however, introduces a trade-off between measurement precision and the experiment's runtime, which can be controlled via a job isolation policy. To analyze the impact of parallelization, we use the best Nginx Unicraft combination to explore the impact of different NUMA core scheduling policies. Each experiment requires 3 dedicated cores, one for the VM, V, one for the QEMU virtual machine monitor, Q, and one for WRK, the HTTP benchmarking tool, W. Our server allowed for up to 6 parallel experiments execution simultaneously. We explore 4 job isolation policies, pinning all instances on a core or on the same NUMA node and pinning one instance on the other core, separating the NUMA nodes between the instances. Flexible isolation policies can reduce resource fragmentation and increase experiment parallelization, but can decrease the measured performance. This figure demonstrates that the request per second and total memory accesses via the Intel PMU counter measured across 6 parallel experiments. Experiments which can achieve relatively high performance results with a flexible isolation policy, as long as the virtual machine monitor and the WRK benchmarking tool instances are on the same NUMA node. Scheduling them on separate sockets results in a 20% decrease in performance due to the increased number of remote memory accesses. Network buffer allocation on the network interface card offloadings are implemented on QEMU's virtual machine monitor, thus maintaining memory locality and can greatly reduce access latency. It was worth highlighting actually that these observations are workload specific. So, in conclusion, tuning OS configuration performance is difficult. Wayfinder can help solve this by intelligently and consistently scheduling relevant permutations. And Wayfinder opens the door for the application of more advanced machine learning methods to the problem of finding optimal system configurations. The problem of optimizing parameters for the OSes could benefit from novel machine learning methods that have been shown promising performance in predicting and modeling the behavior of complex systems. For our future work, we'd like to continue development and extending the configuration engine API. We'd like to introduce methods to improve and control parallelism and performance isolation trade-offs, enabling online experimentation and monitoring. We'd like to continue onboarding more experiments, including the Nginx experiment, and to investigate transfer learning for unseen system. Wayfinder can contribute to this emerging research areas in 3 ways. The first is providing an environment for automatically and efficiently collecting data. The second is to establish a standard method for computing metrics. And the third is performance measurements for machine learning models applied to the problem of optimizing OS configurations. And just to end this presentation, Wayfinder is an open source project and can be found in this link. My name is Alexander, and thank you for listening.